So we said graded potentials, they're initiated by a stimulus, which is usually another neuron synapsing onto our soma. There are small changes in the membrane potential. They can be graded, so the magnitude can vary. It can be 5 millivolt change, 10 millivolt change, 3 millivolt change, depending on the different signals that are coming in. And then it spreads down the length of the neuron by electrotonic conduction. In other words, we have that negative and positive charge that's separated that creates the electrical movement to move this way toward the axon hillock. Okay, now they are decremental, right? The magnitude will eventually dissipate as it tries to move. So if it's a small change that is not negative 55, that will not get here. It will not get here to initiate that action potential. As it moves from where it's coming in and tries to get toward the axon hillock, it's going to decrement or dissipate or sort of dissolute, and it will not create any input on the axon hillock, okay? And that's what we mean by sort of dissipating as it travels. It's not sustained, so it doesn't really reach this area that's so important for determining whether or not we fire that action potential. So we've got the membrane potential here. We've got a small change in that potential, a positive membrane potential change. And then we've got a stronger change, right? Just showing you that this can be graded. It can be a small change, an intermediate change, a large change. And that will basically contribute toward whether or not we are able to create a meaningful membrane potential shift here at the axon hillock, which is at that negative 55, okay? And so what we're seeing at the bottom here is that this is the stimulus recorded at the site of the stimulus. And by the time we get to the axon hillock, that has completely watered down. And so it doesn't reach that negative 55. And so we don't fire an action potential. Now, the purpose of graded potentials is really to help us get to an action potential. So again, it's just a membrane potential change, but it can help us qualify to fire an action potential if we get to that threshold. So if we get to that threshold value, which is negative 55, we are going to depolarize the neuron with enough of a magnitude that we can elicit or incite an action potential. And again, they can be in different directions. So we can have an excitatory change, which is called a depolarization, which is shown here on the far end of this curve. And we can also have an inhibitory membrane potential change or a negative membrane potential change, which is really a hyperpolarizing event or hyperpolarization. And that actually makes it harder for us to get to that threshold, okay? So we'll see different types of signals coming in. Signals that make it easier to get to an action potential via achieving that threshold, which are depolarizing events. And we also have signals that make it harder to get to that threshold, which are hyperpolarizations or hyperpolarizing events. So we have different types or different directions of graded potentials. Now, graded potentials also have the ability to sum. We have temporal summation, which is the same stimulus that's repeated close together in time. So if we have different stimuli coming in on different neurons, submerging onto that soma, if they're close enough in time, we can simply add them together, right? If we have this stimulus coming in at one site, this stimulus coming in at one site, and we add those two together, that would actually constitute a negative 55 threshold change, and that would allow us to fire an action potential. So that is temporal summation, summing stimuli together if they're close enough in time. We also have spatial summation. So these are different stimuli, right? They're happening on different spots of the soma, okay? So not the same spot, which is temporal summation, but different spots that we kind of drew earlier. So different stimuli, but they're overlapping in time. They're happening at the exact same time. Again, we can simply add those values together and sum those, and they may or may not get us closer to that threshold value. So in this example, in this schematic here, we have a synapse coming in at one site W. At the same exact time, right, so they're overlapping in time, we have another synapse coming in at a different site, site Y, and then we can add those two together and determine whether or not we qualify for that negative 55 threshold.